I'll, I'm going to make a note to remind you at the break to pause.
Yes, thanks. Yeah, you can make up for your lapse there.
Yeah.
So a couple of announcements. One is we will end promptly at 11:55, not 12:20 and not 12:30. Two people have to leave at 11 and 11:30. Okay, that's two down. And then 11:55, we have to leave. And the reason why we have to leave, why I have to terminate the class at 11:55 is because, and I'll read this to you. Shoot, there's just too many emails. Really are. Anyway, without finding that darn thing to read to you, what I'll tell you is that the Rotary Club of Montecito, apparently, this is unbeknownst to me until about a week ago, maybe 2 weeks ago, gives out scholarships to City College students. I think they give out 8. I think I saw 8 students from different disciplines get scholarships just for, being good students, or they get nominated. So we were asked, we being the construction tech department, were asked to nominate in an email blast from the Rotary Club to nominate a student. First, I thought it was students, and then I read it carefully and I realized it was just a student. And so Pat and Jim and I got together and nominated this guy that has been in the construction tech for a few years. He's been, he works full time, so he's been slowly getting his classes and credits to get his degree, his AA degree in construction tech. And anyway, we nominated him, and he got it. And so he's getting $1,250. He's getting a check for $1,250. And there's a little ceremony at noon today. It's a Zoom meeting. Is that Yasmin? So I got to be there because I've got to introduce him, and we're going to say a few words. I'm going to say a few words about him, and he's going to say a few words. And we're the only ones speaking out of 8 people. But if you think about it, 8 people, $1,250 a pop, that's $10,000. So they're giving up $10,000 every year. I don't know where the money comes from. It's probably from Rotary Club donations, or maybe they have fundraisers or something. But think about it. If you are involved in City College next year around this time, April, May, ask about this Rotary Club scholarship, because it could have been one of you. I mean, I was asked for credit classes, so at this point it wouldn't have been you. But if you are in any discipline at City College next spring, and if you remember, ask your instructor or instructors about this scholarship. And just by asking about it, you could be the one, because pretty much we just came up with one guy we liked. We like his attitude. We like that he's been here a while. We all know him. We put him up, and bam, he got it just like that. I mean, who doesn't want to wake up to a $1,250 check in their mailbox? Boy, I do, but I'm never going to get it. That's okay. I had my shot. We're going to do a safety meeting. I told you about Aurelio. I told you that we're ending at 11:55. We're going to do a safety meeting, and then maybe a couple things before Albert Brooks. And then we're going to hear from Albert Brooks. He's going to present to us. He's from a company called Small Planet Resources, I think. And he's going to talk to us about ventilation 101, which, by the way, I am so excited about ventilation. That's not the right word. We had a presenter on Saturday, another guy from this Tri-County Regional Energy Network from up in the Carmel area, that talked to us about passive houses. And so many interesting concepts and ways of building that reduce energy use and create passive systems that keep on working, that you don't have to contribute energy towards. just really interesting stuff. And this guy, Albert Brooks, is part of that 3C REN. And so I'm really excited to be hearing about what he has to say. And the stuff about the ventilation is the stuff that I thought was the most interesting. And if anybody's really interested in that, I mean, it's like, oh yeah, ventilation, I really want to know about it. Or if it comes up, if any of you'd like the PDFs, I have PDFs of the PowerPoint that Jay Gentry did and the one before. Wait, we did Green Building Careers, right? On Thursday, yeah. Yeah, so that same outfit, that Green Building Careers. So if you ever want a PDF of that, just let me know. And this guy I mentioned on the Passive House guy. And then Albert Brooks today probably will have a PDF of his thing. So let's see. Do we have Yakub? Did you come? Did you show up? Yakub? No? Wow, Francisco, you look so clear. Yeah, no Yakub. Huh? How about Hector? Hector, you show up? No? Okay. Okay. Let's do a safety meeting. Safety. I don't think, we haven't done this one, right? I keep, because I get confused sometimes, more than sometimes. But I don't think we've done this one.
I think we did actually, first aid.
You-
We talked about like how important it is to have a first aid kit in your truck.
Okay. So
Maybe we did.
Okay, so we did talk about first aid. That's fine. That's fine, because I'll bet you that we didn't talk about cement cleaner mix, cement mixer cleaning maintenance. Not very much fun. Falling objects, you guys pick. Falling objects, you like it? Preventing electrical accidents. Oh, how about that one? Do we do that one? Anybody remember that one?
No, we didn't do it. Let's do that. Preventing electrical.
Yeah, 'cause that would be, I think that would be very germane for what we're doing right now. By George. Okay, I'll read the introduction. Electrical, preventing accidents, introduction. Human error, poor maintenance, improper equipment design, and lack of training add up to disaster when it comes to electricity. To protect workers against the hazards of electricity, they need to know the basic facts about the causes of shock and death. Brianna, would you read for us, please? Water and electricity don't mix.
It's not the voltage that kills, but the amount of current that passes through the body. The condition and placement of the body has a lot to do with the chance of getting a shock. Water and electricity can be a fatal combination. Damp areas and metal objects can offer good shortcuts for electricity to reach the ground. Sweaty hands, moist or damp socks and shoes, a wet floor can and will allow a current to pass through the body. In wet winter months, extra caution should be observed when working with electrical equipment or when working near grounded objects.
Okay, how about Luis for shock prevention?
Wear rubber gloves and boots when working near water. Use rubber mats to stand on. Use insulated tools. Use rubber sheets, which can be used to cover exposed metal. Treat every electric wire as if it were a live wire. Inspect equipment and extension cords before each use. Faulty electrical equipment should be taken out of service for repair. Do not use tools or electrical cords that have bent or missing prongs. Make sure your tool is grounded if there aren't 3 prongs on the plug or if the receptacle doesn't have 3 openings. Turn off the power and report the smell of hot or burning plastic, smoke, sparks, or flickering. Stop using a tool or appliance if a slight shock or tingling is felt. Never disconnect an electrical plug by pulling on the cord. Make sure the circuit is turned off and locked out at the circuit breaker or fuse box when working on an electric circuit. Only trained personnel should work on circuits. Those who regularly work on or around energized electrical equipment should be trained in emergency response and CPR.
Yes, they should. And if an electrical accident occurs, how about Anthony? Okay, how about Sam? Sam, you there? Sam Greenberg? Saw you check in. Okay, Levy.
Do not touch the button
Victim.
unless you are sure that the button is not still in connect with the electric hazard or the electrical has been switched off.
Yeah, if the victim is still getting current running through their body to ground and you touch them, that current will jump right to you and to ground. Go ahead.
Remember to check the wires, fire, gas, glass to protect yourself from any hazard before touching the victim.
Yes.
If you are unsure of how to do this, get quali-
Qualified.
qualified help without delay.
Delay.
If the victim has been removed from the all above hazard, check for breathing impulse. If breathing or a pulse is absent, call for help and
Initiate. Initiate.
initiate CPR without delay.
Without delay. Okay, and so as a vocabulary word, initiate, if any of you aren't familiar with it, it means basically start. So call for help and start cardiopulmonary resuscitation without delay. Conclusion.
I can read the conclusion, but I think my mic wasn't working.
Okay, cool. Would you please? Thank you.
Yeah. Conclusion. Think safety. When doing anything associated with electricity, water makes up most of the human body, which makes the body an electrical conductor. An electrical current running through a body can range from a slight tingle to burns on the surface and or deeper within the body to a harmful and potentially fatal electrical shock.
Yes, it can. And so here's how electricity works when you get shocked. It travels through your body to ground. So if I grab this water bottle here, and it's got 110 volts, got a live wire that's shorting and that's putting electricity out into my hand, that current's going to go through me and look for ground. If I'm not touching anything over here, it won't find ground here. It'll go down and find ground down below me. So I might get lucky. It might ground and go straight down and not pass through and across my heart, because that's how your heart stops. If you get really unlucky, is you'll grab this and you'll grab that and you'll ground hand to hand, and it'll cross straight across your chest, and there's a good chance, or there's a chance it'll stop your heart. So just, you don't want to get shocked. There's minor little tick shocks, and there's shocks that blow out big holes through your heels and everything in between. So electricity is dangerous, really dangerous. So please be careful when working with it, and just make sure you're not working in water, be insulated. And if you're not familiar with electricity, don't mess with it. Get somebody that is. And even the people that are super familiar, like Rick Harrington, this guy, this electrician who's forgotten more than most people I know about electrical. This guy was working at UCSB high up and got shocked with 440, blew him off a ladder, turned his hair completely white, blew out the palms of his hand. I mean, he's alive, but I mean, it was horrible. It was horrible what happened to him.
Blew out like the palms of his hand.
Yeah, the electricity, when it came out of him at 440, it's such a big current, it blew out the skin on the palms of his hand. Sometimes when it grounds through your feet, he must have grounded to a ladder. It'll blow out through your heels, just big holes in your heels. Usually people die. So he was electrocuted. He just didn't happen to die. Anyway, the point is.
What do they do with his hand? They like graft skin onto his hands? Where the holes
Exactly
are?
right. Exactly right. The graft skin.
Oh my gosh.
Yeah. It's
And
not
can he
pretty.
like walk Can he walk and like function okay and move?
Yeah, I took him, he
No?
had to do rehab. This was 30 years ago.
Yeah,
But,
yeah.
yeah, it changed. He still kept working on electrical, you know, you just gotta be really careful. Yakub, I got you here, buddy. I got you here. The only one I don't have here is Hector.
Thank you.
No Hector? Okay.
Hector, no, he usually comes in like around 10 or 10:15.
Yeah, okay. All right, we got 7 minutes until our presenters show up. Let's see what I got here. Let's see, we got some chat. Gerardo, Carla, nope. Can you hear me? Sam, okay. Okay. Let's go to intermediate construction electrical, week 2, 5-4. Hey, that's today. We did our first aid meeting, which really wasn't first aid. We're going to have this ventilation 101 by Albert Rooks of Small Planet Supply. This is a fairly short video. Let's just see this while we're getting ready for Albert to fire
Now,
up.
as we pulled out the outlet, you can see here, we noticed something here. See this right here? This is, they took the ground wire, Now, as we pulled out the outlet, you can see here, we noticed something here. See this right here? This is, they took the ground wire, didn't even leave any decent parts of it. It was copper, and they just wrapped it around a painted part of this screw boss here. That is a lesson, folks, in how not to ground an outlet. This outlet is not protected. It is not grounded. So anyway, we're going to be putting in a new outlet switch. And remember, this is a metal box. So we need to make sure that this metal box is grounded and bonded to the system ground. We're going to put a green ground screw right there. See that hole right here?
Yeah.
That's meant to house a green ground screw. We're going to wrap this copper wire around it and connect it up properly to the new switch.
Hey everybody, Jeff here, and welcome back to our channel. If this is your first time visiting us, this is a great time for you to take a look at the subscription button down below. You want to click on that so you can be aware of all of the other videos that we put out to help you. So this is all for you, my friends. And at the same time, when you subscribe, make sure you click on that bell icon right next to it that will appear when you subscribe. Because it doesn't make any sense if you subscribe without being alerted to every time we put up a new video. Okay? And then if you have any questions at all, leave them down in the comments and we'll answer them for you. So let's get started with today's project. Okay, so now let's show you the proper way to ground one of these boxes. So we're going to have to clean this off first. So I usually use this blue emery sandpaper tape here. This is what the plumbers use.
So that ground wire is not insulated, right? It doesn't have insulation on it. It's just copper wire, and that's typical ground wire, but it's painted. So it's effectively insulated, and that you won't get a ground off it. So he's sanding the paint off is what he's doing.
We're doing a little abrasive sanding on the pipes before they solder. So see how this is nice and shiny copper now? That's how you make a nice, good conductor. Just like that.
So you can see what we've done is we've wrapped the wire around a ground screw now. So now this metal box is going to be, it's already bonded to the system ground. Then if you look here real close, see how the way they ran those wires in the back of the switch there? That's a big no-no. Look how much, he's left almost 1/4 of an inch of bare exposed conductor. That's a major, major no-no. And this is what we find a lot down here with the builders. Like I said before in our other videos, the builders overcharge you big time, and this is the kind of quality work they give you. They just hire the lowest paid, dumbest guy in the world to do all their work, and this is what you're left with. So we're going to put a better switch in anyway. We're going to be putting this switch in. And you can see it has its own ground screw on there that we're going to connect it up to. So let's fix this problem right now. So there you can see we finally got it connected.
So that's a rocker switch. The other one that he has, God, I can't think of the name of it. but those larger switches are Decora switches, or call them Decora switches, DECORA, or it's a rocker switch. They're more contemporary. They look a little better. They're easier to hit than a small little switch up and down. You just hit that whole plate and it does the switching.
We added a pigtail wire because the amount of ground wire that they gave you was too short here. Same with their black and the white wires were too short. I mean, these guys are so dumb. It's like any chance they get to violate the National Electric Code, they will. They're supposed to have 6 inches of wire.
Hey, tell it how it is, bub.
So because of that, because of their foolish mistake, what we did was we had you can see back in the corner there, we stuck in one of these
Wow.
Wago wiring nuts, and this is what they look like. So you put the 2 wires in there, and then you snap the doors down,
Nice.
and it holds the wires together nice and tight, so you have a nice tight connection.
It's a wire
And on
nut.
the other end of this pigtail over here to the outlet.
Where's a wire nut?
Fine. And it's okay if the ground here has a little bit of insulation. Deal with that. That's not a problem because there's no conductor. It's not carrying. So now I'm just going to see if I can get a piece of black tape, green tape, electrical tape wrapped around the outlet because I only like to cover the terminals to protect anybody who comes in later to do any work and maybe they leave the power on or something. And before I do, I wanted to show you how I wire it. See how?
So I've never seen this guy here before. Typically, we use a wire nut, and I am going to stop this video for now. Stop the share. Pin myself. That's a wire nut. That's one example of a wire nut. There are ones that look different that don't have these little wings on them like that give you a better purchase with your fingers. There's ones that don't have the wings that you just go like that. And you put 2 wires in there wrapped around each other, 2 or 3 wires, depending upon the size of the wire, what you're wire nutting together. And then you just turn that clockwise and that twists the wires together and it joins those 2 wires, just like the device that you saw in that video. So let's see if our presenters have arrived. Sean's here. Is Albert here? Sean?
Albert is here.
Oh, Albert's here. Hey, Albert.
Hey.
So can we see your video, Albert?
I think we can. So let me try seeing if I can share. I think
I'm going to make you, Albert, I'm going to make you, let's see. First of all, I'm going to make you a co-host so you can share screens.
Great.
Is that what I should do, Monica? Or should I?
You can do that, or you can just allow multiple participants to share on your share screen. Either one.
What's in that? Where's in that? That's in
Go
share
down
screen.
to the green arrow where it says share screen. There's a small arrow.
Okay.
Click on that and choose.
Okay,
multiple
done.
participants.
So I would like to introduce you to Albert Brooks. And Albert, I would like you to please tell us, do your shtick and give us your bona fides and your bio. And really, right at this point, Albert, the floor is yours. I will say one thing though. It's 9:30. I try to give a break to the class at 45 and 50 minutes, about somewhere in there, 55. So if you get to a place, Albert, about 20, 25 minutes, half hour into your presentation where you feel like you could break for even 5 minutes, that would be great. And I will
no problem.
find you if you forget. So right now, please welcome Albert Rooks.
Great. Thank you very much. So we'll run a little bit and then we'll take a little bit of a break. This is, this is really meant to just be a little conversational and a little interesting about a couple of subjects. So we'll just kind of keep it light like that. So I work in a business called Small Planet Supply. And it's a business that we started about 10 or 11 years ago. And it really, for me at that time, it was really about how to take buildings and make them fit kind of the climate problems and the sustainability problems that we had at the time. And I became interested in a thing called Passive House, which are these really super high performing buildings. And sorry, I got to figure out how to mute a phone there. And then I just kind of stayed with it, and it became a very interesting journey. And so part of what we do is we just look at buildings and how they're put together and how to make them work better. And I've really had just a whole lot of fun doing that. So today we'll talk a little bit about ventilation. Questions. My wife Eva is on the line also, and questions at any time are just fine. This is meant to be interesting and fun. So we have no particular schedule. We really have to work. And so essentially what we do is we try to make buildings have a very small impact on the environment by making them efficient. It's all the same principles. Anything we build today in a building, we've got basically, a couple, 2-3 things we're trying to accomplish. We're trying to make a building enclosure, the walls and the roof and the windows and things like that, is something to separate us from the environment outside. And so we build it in different thicknesses with different characteristics and things. And then once we're inside those buildings, we kind of have some needs. And one of the needs is to maintain a reasonable temperature. So we put in heating systems and things like that. And then the other thing is, because we're human beings and we need air to breathe, we need to provide ventilation in those buildings. And so what's happening in the industry these days is, because, if you make a little bit of heat in your home and it's cold outside, you start losing that heat. And the way you improve that is you just add a little better insulation, or you make the building a little more airtight. So when the wind blows, it doesn't kind of push the heat out of the building. And so, as you're wiring up your Decora switches in those outlet boxes and things, there are things you can do to kind of seal where those wires go through, which could actually, get to the outside of the building in a little bit of heat loss and so forth. But where I'm kind of going with this is, once you make that building, a little bit tighter, people need air. So what we're really going to talk about is just the basics of ventilation. So there's me with my wooden cup, with a friend that's got a machine that makes those wooden cups. And so my history is I've taught a lot of ventilation classes because a lot of what we do is new to the market, and people don't really know how to do it. They're used to building the basic homes that we build right now, which we all want to do as well as possible. But as we get new ideas and we want to implement those on buildings, then we need some kind of an instruction and class to kind of make that practice work. So we'll just take a quick look at ventilation here. And the ventilation is an answer really to homes getting a little bit tighter. And when I say a little bit tighter, it means that, now we're kind of sealing the electrical outlets, we're sealing the exterior sheathing of a home, and just plug in those little air gaps, right? If you just thought of a home as a cup, and you turned it upside down so the roof points downward, and you filled it full of water, you'd see just a whole bunch of little water leaking out of various parts of the house at the windows and the doors and all those things. So tightening it up is just finding those and sealing them up. Once we seal them up, ventilation is really important. It's not just about getting cooking smells out of the kitchen or out of the bathroom or something like that. As humans in these buildings, we need fresh air to survive. And maybe survival isn't really the benchmark we want to use. We all know that if we're in a classroom and there's a whole lot of people and it's winter and everything's closed up, sometimes you fall asleep because there's too much CO2 in the room, right? Everybody's breathing, making CO2, and there's not that much fresh air. And that has a bad health effect on you. And the same thing happens in homes when they're all sealed up without proper ventilation. So we want to manage conditions to make them livable, but we also have the opportunity to manage conditions to make them so that people in them can flourish and be really healthy. So manage CO2 and moisture and volatile organic compounds, or VOCs, allergens and mold and things like that. It's kind of funny that these beautiful old houses just don't have any airtightness at all, and they do really well over time. And that's because just the way they're built and kind of how leaky they are, it keeps the wood in really good condition by not trapping moisture and things like that. These days, we don't build them like that anymore. And as they get tighter and we get inside the building and we shower and cook spaghetti and make more moisture, the moisture can kind of get trapped and it's kind of hard on the building. So as the buildings get tighter, we think about ventilation, A, as something to keep people healthy, but also B, as something to keep the building healthy. And all that really means is injecting a little bit of air into the building on a regular schedule. So lots of different ways to make buildings tighter. And this friend of mine standing there grinning in front of that red door, that red door is just a tool we use to measure how tight the building is. That white round thing at the bottom is actually a fan behind it. And the fan's hooked up to a little control, and it'll move air through the fan, and we'll measure how much air moves through, and we'll know how leaky the building is. Another thing that happens is we live in a changing climate. And so creating buildings with ventilation that can also manage the smoke kind of coming from outdoors to indoors is something we're interested in, because smoke is a real thing, and it's something we're going to have to contend with. And we want to think about ways that we can create tight buildings with ventilation that manage smoke events and things like that. And all of this is really just to say that as we start with a foundation and we put up walls and all the rest of the 10,000 steps that it takes to build a building, even adding that wire nut onto the wire, which penetrates through the box and goes in the wall and so forth, all those little steps are important, and that they all contribute to how well we can manage the building in respect to ventilation also. So that blue zone in the middle is really kind of where we as humans want to live. And this is a gauge of relative humidity. So on the left side of the blue zone is a dry house and a dry climate, right? So if we go out to the desert, we're going to be in areas that have, really low relative humidity. And if we go down to Atlanta, Georgia, or Florida, or something like that, we're going to be areas in really high relative humidity. And with ventilation tools and buildings, we have a way of managing a building to kind of stay in that blue zone. So as we build them and as we think about ventilation, we think about it in a way that will guide the air quality that we live in back into that blue zone. And there's ways to do that. Today we don't have to take a deep dive in how we do that. We just want to acknowledge that we can kind of take control of that to a degree. Also, in tighter buildings, we want to think about all the things that we carry inside of our buildings and then begin to live with. And everything that we do inside these buildings, as they get tighter, all stack up. And we as humans don't really want to be around pollutants and too much moisture or too little moisture. We don't want to be around too much CO2 and all these other things that can tend to have a negative effect on us. So again, as we put these buildings together and so forth, all the little steps and all the materials that we use kind of matter. And there's a whole movement, the green building movement is very much about, as we bring materials inside to a building to construct a building, that we make sure that we use the friendliest things possible.
Hey, Jay, I'm sorry, Albert.
Yeah.
Could you please tell us what PM10 and 2.5 are?
Yeah, sure. okay, I'm probably going to butcher this a little bit, but those are sizes of particles. So when we look at a smoky day in fires, I'm just going to point to that.
Parts per million.
Yeah, parts. Thank you. Parts per million. So 2.5 is, I believe, 2.5 microns in size, and it goes, and the sizes range to large, 10 microns, all the way down to 0.003 microns. And in discussions with ventilation, smoke and ash is right around that 2.5 and larger to 3 to 4 microns. And, things like COVID are way down there at the 0.001 to 0.003 range. And these ventilation devices all have filters that to some degree can capture those and keep them from going into the home, or when they're in the home, they can capture them and keep them from spreading. And it just has to do with a fact that maybe I can get my screen back to the back. Oh, I'm going forward. I'm going the wrong way there. There we go. Okay, so that down there in the lower right, PM10 and 2.
So that probably means particulate matter, right? PM, particulate matter.
Yeah, I believe it does. I know the abbreviation and I kind of work with the numbers, but I haven't honestly spent a lot of time thinking about kind of what that PM, whether it's parts per million ppm or particulate matter 10 and 2.5. Yeah. Yeah,
Okay,
thanks for that.
So your wife just chimed in, which is wives is great for, and
Yeah,
told us what's
great.
really happening, right?
Yeah, thanks, Eva. Yeah, she says, yes, it's particulate matter.
Thanks.
There we go.
And that's 10 and 2.5 microns.
Yeah. And then, so in some cases, we're looking at 10 as being extremely large, right? And something around that size is floating in the air and you can kind of almost see it. 2.5 is kind of like that gray smoky haze, 2.5 and larger. And there are filters and equipment that will filter that out and it becomes more important. And then we work in an environment where we're even reaching below the 2.5 down to very small particle filters that would be like a HEPA filter is a very common term, and that's trying to filter out something that's 0.01 and smaller. Yeah, okay, good. There's a nice.
I was just asking because 2.5, I mean, we live in California. There are a lot of wildfires. There have been that we've had that experience the last couple of years. 2.5 would be like when there are wildfires around here and that ash is in the air and getting into our homes.
Yeah,
it is.
And more.
Yeah, so
and above.
So we work with ventilation equipment and filtration and so forth. And for the last few years, I'm beaming in today from the Pacific Northwest in Olympia, Washington. Same problem, lots of fires. And so there's two different things going on, right? So California right now, as you put in ventilation equipment, the new Title 24 regulations are that you put in a MERV 13 filter. And so on the MERV scale, 13's pretty good, and that's what you got to put in. So what MERV 13 will capture when there's a fire in the area are kind of the large particulates, and when you inspect your filter, you'll see that it becomes, kind of dark gray and black, and you're picking up a lot of material.
Yep. What
you're really not aware is that the actual ash that's harmful to your body is also quite a bit smaller. So while we're capturing PM 2.5 or that size particle, there's a lot of smaller particles getting in, and that's where people started deploying HEPA filters inside and measuring their interior conditions. So there's a scale, but it all does start with PM 2.5. And back, the basis of this conversation is that the ventilation is a way to bring air from the outdoors in through a controlled pathway into the home that you can regulate how much you're bringing in and running it across the filter. And if the rest of the building has got some good air tightness and is put together well, then all of that works. If the rest of the building is really leaky, then, you know, there's other pathways that ash and contaminant can get in. So
I have
moving
one more
along.
question, sorry. There was a picture right before that where it said 9:09 a.m. and it looked like nighttime and it was dark. Is that from a fire as well?
Is
Or
that from
what
smoke?
was that picture?
Yeah, so
That's smoke.
that's a friend of mine in Prince George, British Columbia. That's Friday, August 17th in 2018, 9 a.m. downtown Prince George.
Wow.
And, you know, I haven't experienced this so much in Washington State, but I saw a few friends with pictures in California, you know, depending on where they are. And yeah, this is really happening. And this is, you know, in our business, this is something we're dealing with on an annual basis. And trying to come up with new ways to filter that air, because, you know, essentially when that happens, right, the first desire is to close up the building and keep that stuff from coming inside, which means you have no fresh air.
Yeah.
So the ultimate, you know, kind of the best situation is to create a level of filtration where you can keep getting some low quantity of air coming into the building that's running across a filter and giving you something reasonable to work with.
And just as a quip, Albert, if 9:09 a.m. in Prince George, if it was December 20th or 20 somethingth, would probably be that dark, right?
As a quip, no, it's not that far north.
No,
it's
okay.
not that far. We haven't hit the polar circle yet.
Okay.
Yeah,
Alaska.
I haven't been there in December, but I think we have some light at that point. So anyway, okay, so here, human body, right? All the particulates that we can't see after they get smaller for PM 2.5 really matter also. So if we have a way of controlling that and it doesn't get through the rest of the building envelope, then we're one step closer to creating a good environment. Here is a friend of mine's house on the Monterey Peninsula.
Jay Gentry?
Not Jay Gentry, a guy named Bill Hayward.
Okay, I know him really well.
Okay, all right. So you know Bill. Okay, so Bill built a new house, and Bill's been in the lumberyard business, and he works with Hayward Lumber, right? He's a Hayward Lumber family member, runs the company right now, right? So 100 years of building material. And he says, I want to build a building that is really super, super healthy. So I'm going to look at everything that comes in, right? I'm going to use plywood. I'm not going to use OSB. I'm going to use kind of the best timber grades I can. I'm going to pay attention to what kind of pressure treated lumber and you know, kind of all those things, no carpet, blah, blah, blah.
FSC, yep.
Yeah, okay. So he does that. And he sets up some data monitoring. And he runs the data monitoring, and in a normal condition on this home, the parts per billion of the total VOCs in the building are running here right around less than 200. It's looking really pretty good.
Yeah.
And he's got a ventilation system going, right? So he's got a really airtight home. He's got ventilation coming in, constant source of fresh air coming across some MERV 13 filters coming into the home. And so far it's looking pretty good. But then he turns off let me see if I can get my slide to advance.
Holy smoke.
Okay, so now he turns off the ventilation system, and the ventilation system is what's known as balanced ventilation. So if you've got a certain amount of air coming in, you've got an equal amount of air going out. So the house is in balance and we've got a steady airflow. And when we turn that airflow off, basically the air quality deteriorates at an alarming level very, very quickly. So here's a guy that was very careful about the materials that he brought into the house, chose the best materials that he could, and the air quality climbs up, or the air quality deteriorates, as shown by that peak, all the way up to 1700.
Wow.
And then we turn the ventilation system on, and almost immediately it drops down to below the World Health Organization, 500 parts per billion, and then settles back in right around its 200 level and keeps cruising. So this is just an illustration, right? We're working on the buildings that we're working. We don't get to make every choice that of all the materials that go inside of the building, but the one choice that we can influence is the ventilation across the building. And as we push air into the building and bring a matching amount of air out of the building, we carry along all those pollutants, excess moisture, and we start creating a really good safe space for people to thrive in. So that's just kind of a quick share on how ventilation works. Now we'll we're 25 minutes in. How about if we just take a quick 5 before we get into the types of ventilation?
Let's do that, Albert. Let's go. I have 7 minutes until 10. Actually, I have 6 minutes till 10. Let's just come back at 10 straight up.
Yeah, that sounds great. I'm just going to leave my Zoom open, and when everyone's here, we'll start back up.
Okay, it's a deal.
And ventilation really comes in 3 forms. There's supply only, where essentially we have a building and we take a mechanical fan or something like that, and we inject fresh air from the outdoors into the building. Once we kind of dive in, we can see that we can direct that air to certain places. But if you just think about the building as a box, we're going to inject fresh air into the building. It's not a perfect solution, not my favorite solution, and I'll share a couple of reasons why I think that. Second method, which is the most common, this is what I grew up with, is exhaust only. And exhaust only is just the reverse of supply only. Our building is a box, and we have 1 or 2 or 3 or 4 mechanical fans that are just pulling air out of the building. And normally we'd see that in a bathroom with a bath fan. Maybe it's set to run for 20 minutes, or we just turn the switch on or off and it runs for an indeterminate period of time. And what happens with exhaust only is there's supposed to be some place for fresh air to come from the outside into the building. And as we look closer at exhaust only, we'll just talk a little bit about that. And then lastly, there's my favorite. This is the one I work with really exclusively every day on very, very high performance buildings, which is balanced ventilation. And balanced ventilation is just simply the combination of supply and exhaust in running equal flow. So there's a mechanical fan or some source of supply air flowing into the building and a matching source of exhaust air leaving the building. And as you start looking closer at balanced ventilation, you can start to see things like, well, I really would like my fresh air supply or some of it to show up in the bedrooms or the dining room or family room where people are gathering and they would like fresh air. And if I've got to have some exhaust flowing out of the room, I might as well pull it out of the bathrooms or the kitchens or something like that. Yeah. So we'll take a quick look at each one. No big deal here. Supply only system is essentially a fan or a series of fans that is injecting fresh air from the outdoors into the building. It generally creates positive pressure in the building. So if we have a lot of moisture or we have other things going on in the building, essentially what can happen is it will bring the air in at a steady rate, but we're not really sure where it's going to go. We can kind of know where it's going to go. It depends on where we actually point it and what kind of ducting we build to deliver it to what purpose. But because if we add X quantity of air, which is measured in cubic feet per minute, so if we have a building and we inject 60 CFM into it, we also have to have 60 CFM leaving. Otherwise, the building is going to blow up like a balloon and we'll have other problems. If we have too much moisture, what can happen is we'll push that moisture into the walls and the assemblies. If it's cold outside, building science will tell us that the exterior members of the building can become cold, and that water that gets pushed into the walls can hit that cold surface, and just like a pop can on a summer day, turn into liquid water with condensation and create some long-term building damage. So supply ventilation is, okay, we're getting fresh air. We're not 100% sure where it's going. We're not really controlling, and we're not creating a pathway out. And if we are, then okay, sure, we're getting some air. We've got a pathway out, maybe not the most perfect situation. Exhaust only, same set of problems in reverse. We've got some relative ducting. We've got one or multiple fans in the house, and we turn the fans on all the time or just part of the time, and we suck air out of the house. To suck air out of the house, there's got to be some kind of makeup air.
Yep.
And today that makeup air comes through the cracks and crevices of the building, even through those electrical switch plates where the wall joins the foundation that it's sitting on, or where the wall framing joins the floor framing. And in some time in your career, you'll open up an older house, and that older house might have batt insulation, and you'll just see this wonderful pink insulation has just turned gray and black and nasty. And that's all due to air leakage, right? So there's always stuff floating in the air, and as it travels into the wall, moisture or dust or whatever it is, it will get trapped into the wall. And that's how moisture winds up getting in the wall, and the insulation gets discolored, causes some problems. So that's really what happens with exhaust. It's simple, cheap to do because it's buying bath fans and maybe a whole house fan, and it's easy to set up, but it's not really that awesome of a tool for ventilation. Another issue, the extreme issue, is that in my climate, if we have that fan and we're sucking air out of the house and we're pulling air in from all the imperfections around the building, on a wet day with lots of moisture, we're pulling in moisture. So just because we have this negative pressure happening in the building, and on the exterior plane of the building, we have liquid water, we can actually kind of pull that water in. It creates a lot of interesting situations. And another situation is, if we're pulling air through imperfections of the building, we're not really able to run any filtration like a MERV 13 filter, or really any kind of filter to capture smoke or other particulates. Balance ventilation.
Albert, can I ask you to go back on that
Yeah.
slide? What are these three things on top of the roof that are drawing air in, bringing air in?
Pot lights.
Oh, okay, so down lights. So they're can lights.
Can lights, yeah, sorry.
Not insulated
lights
around. Okay, gotcha.
Yeah, pot lights is the Canadian term, and we've taught air tightness in Canada, and boy, they love their pot lights up here. Down here, we call them can lights, and boy, we love our can lights down here
We
too.
do, and so I see that it's bringing in from the unconditioned attic. It's drawing in. Okay, got it.
Yeah, right. So that unconditioned attic, boy, you know, and there's just nothing about this we like, right? There's scenario after scenario. Like we've got a house in a location, and it's 87 degrees outside. And we've got an air conditioner on inside the house. But that roof attic is super, super hot, right? The sun's hitting it. It gets, it gets really quite hot up there. And because we have the exhaust fan running, we're pulling hot air out of the roof cavity into the interior space, where then we have to cool it back down. And at the same time, after we cool it back down, we're sending it out of the building through that exhaust fan. So we're just kind of bringing in air that needs to be reconditioned and reworked, and sending it back outside of the building. Whereas balanced ventilation is, we have the opportunity of doing some air tightness on the building envelope, and now we have two fans. We have one pathway that brings fresh air in from outside of the building, which gives us the opportunity to run it across a filter. We can set up some ducting or distribution to run it into the building and deliver it wherever we want to. And in our world, we're very, very specific on how we do that. And then at the same time, we've got another fan running basically the same speed or the same airflow rate. And it's gathering exhaust air from areas in the building that we would like to remove the air from, such as kitchens and bathrooms and mud rooms and things like that. Craft room where we might be working with some, smelly glues or something like that. So when those two flows are running at the same rate, the building envelope isn't under pressure. So unless there's an extreme amount of wind or something really pushing a force of air leakage through, we're not pressurizing the buildings, so we're not pushing anything out through the walls, and we're not depressurizing the building, so we're not sucking anything through the walls. We're just kind of working in balance. And there's a really cool thing that happens with a balanced ventilation system is as we deploy balanced ventilation, we can do something called heat recovery. There's one more little feature. If we put those two fans in the same box, and we put this basically a heat recovery core, which is it's just kind of a funny shaped thing made out of various materials where one airstream that is leaving the building is maybe 70 degrees, and it's passing right next to another airstream that's coming in from outside of the building, where in my neighborhood, it might be about 45 degrees. And what happens is the heat moves from the 70-degree side across a system of plates to the 45-degree side, and it warms the 45-degree side up to 66 degrees, recapturing most of the heat that we've already put in the building and delivering that heated air from the building energy that we already put in into the building.
So Alvin,
yeah.
sorry. So this
Please.
is a separate system. It's completely separate from your air conditioning or your forced air system, correct?
Correct. It's just ventilation. And the ventilation has the opportunity to gather the heat that we already put in the building and transfer it onto the fresh air stream that we're injecting back into the building from outdoors, which then means we're keeping the energy that we put in the building already in the building, which then means we just don't need to heat the building as much. So we need a smaller heater, or we need a smaller air conditioner.
Jay has a really good animation of this this principle showing a pipe split in half, right? Metal pipe split in half with the metal piece splitting the pipe in half, cold air coming in, warm air going out, and the heat transfer is over that conductivity of the metal over the length of the pipe. That's essentially what we're talking about, right?
That's essentially what we're talking about. Yeah, and I never we talk about that quite a bit, and if we'd like to really dive in deep on an occasion, then we've got materials to really dive in deeply with that. The equipment that I work with is the equipment that Jay and kind of the other Passive House California builders work with, and that's where we really spend our time for the most part. And it really works. It's literally how you can make a single family home and heat it in the winter with a few candles. And it's a fine little statement, but I know somebody who's done that, right? Power went out for a week. They're in Illinois and they kept it going with 6 candles because it's really that good.
Well, what powered their system if the electricity went out, or did the electricity go out?
Well, so nothing. The building stopped working, but the envelope was so good, the heat loss was so good in the winter that their activity and warming themselves, I don't know if they still had domestic hot water, if they had a tank that they were able to use and so forth, but literally the input of burning 6 candles kept it above, like the low 60s when it's, approaching freezing outside.
Well, That's incredible. That's incredible. Tell me again, please tell us, what is that system called? I mean, we're looking at a balanced ventilation system, but then if you go the extra mile and do that crossover, what's that called?
Heat recovery ventilation.
Heat recovery ventilation.
Yeah,
People
so
make
that's known as
systems.
an,
You don't
as
have
an
to, you're not reinventing this wheel, right? People
No.
manufacture systems like this.
lots and lots of manufacturers make these. They're available all over the place in California. And they're known as an HRV or an ERV. And the California code is quickly catching up to requiring some form of heat recovery ventilation.
Hmm.
It's just really simple. Essentially, you got two fans in a box.
Yep.
Running the same speed.
Yep.
And a core where you transfer the energy from one side to the other.
Yep.
And I gave you the illustration on a cold day where it moves the heat from the house back over to the supply temperature. And on a hot day, when you're running air conditioning, it does exactly the same thing. It's just,
Reverse.
it's the way physics works. It moves the high concentration of energy over to the low concentration of energy. So on a hot day, it keeps the hot out and the cool in the room. And so when we look at the cons in balanced ventilation, there aren't really any cons. It costs more.
What about the
more
cost?
to
What about the
do.
cost, Albert?
It costs more. But if we spend that money, everybody gains.
Well,
Right.
you're gonna recapture and recoup that money in the long run due to
You are.
lower energy bills, period.
Yep.
But
Yep.
I'm just wondering, is an HRV system for a, 2,000 square foot house? Is it a $2,000 bill? Is it a $10,000 bill? What are we talking about here?
I think the actual equipment is probably anywhere from 3,000 down to 900,
Okay.
right? Because you can get various quality levels.
Right.
And it's really more the labor to install it. That's really where the cost is, right? Because we've got to set it in there, we got to wire it and run some ducting, but the
Right.
equipment itself is really not that much money.
So,
And if we're not running ducting, we're not really ventilating the building, right? We're
Yeah.
just,
yeah, I see that. But I wonder, in just like my house, for instance, I have a crawl space top and bottom. I have an unconditioned attic, I have an unconditioned basement and crawl space. It's a no-brainer for me. I could get this system and install it in both places and have it work without having to add really much in the way of extra ducts, other than I can get in my unconditioned spaces, pop a hole in ceilings, pop a hole in the floor. Can't use the same holes I'm using for my forced air. I get that now, but I mean, I can't believe I've lived this long and not known about this.
yeah, right. So Eva and I did our retrofit here at Olympia, and we did it. We dropped the unit in the basement, we ran the ducting, and right now it creates a really, really nice environment. I could go on for a long time about kind of all the qualities that it creates. Basically, it creates, every day is like a spring day. You just have this beautiful air quality with high degree of oxygen and low CO2 and not much dust.
And you have, so besides the temperature balancing that you're using, nature to provide inside your home, you have 2 points, right? Or at least 1 point that would really be your inlet where you're going to want to filter the air. You don't need to filter the air as it goes out, right?
Yep, correct.
But you have a point of intake where you really have a chance to filter the heck out of the air, which is a problem for us in the wildfires. We want to shut up our houses tight, and if I fire up just my fan for my forced air, it's drawing air in through every crack there is.
Well, so two things. One is, yes, that's absolutely correct. And you can put good filters on, and you can double stack filters. In other words, use the standard filter that comes with the unit and then get a separate filter box with a higher degree filtration. You can get HEPA filters right at Home Depot. But the other thing is, on HRVs, there is a filter on the return air before it comes back to the core, because in order for that heat recovery to work, you need the core to be clean. You don't want it to be full of dust and cat hair and stuff like that. So you actually are cleaning your interior air, right? You've got negative pressure flowing, it's hitting a filter, and you look at that filter a couple times a year and clean it out. On the better machines, it's a really good filter, and you change it twice a year. And it's part of the reason you don't have a lot of dust, and, you know, your animal dander and things like that are minimized. So jumping ahead, right? We're just going to take a quick look at distribution. Questions, comments are always welcome, so jump in. So
Did you
here's some
see that
rude-
one from Ian. Are there air tightness standards you should try to meet before installing an HRV, ERV system?
Yeah, you know, getting to code level is good. HRVs and ERVs really make a strong difference at 3 air changes and tighter. You really have to have them, right? Because once you get a home down to 3 air changes, 2.5 air changes, you really can't depend on leaks in the building envelope.
That's a minute, right? CFM?
Yeah, yeah, cubic feet per minute.
Yeah,
So,
so you want to, so if you've got cubic feet of your house is X, you want to see that times, at least times 2, right? Or times 3, but no more than that.
Yeah, correct. Right. So, and that red door that we looked at early on is the way that's measured. And you're working on a building that air tightness is a factor and people are paying attention to it and working for air tightness, in which case you'll probably get a pretty decent result as long as you just, you know, don't leave any gaping holes and so forth. HRVs and ERVs work in all buildings, whether they have good air tightness or not. They will improve the building because the building will spend a lot of time at its natural resting point, and so we'll get steady flows of fresh air and filtration and things like that. It's just that when the buildings get tight, you really, really need them because here, we look at this floor pan right here. So say I'm shoving 60 cubic feet per minute into this building. And in order for that fan to actually bring in 60 cubic feet a minute, 60 cubic feet a minute have to leave. And at some point I get that building envelope so good and the windows are shut because it's December that it's really not going to be able to push 60 cubic feet per minute in because there's no leakage. There's not enough leakage for it to leave. So it really does matter that as the buildings get tight, we create a balanced ventilation rather than exhaust or supply only.
Yeah.
So supply only, we don't really know where that air is going to go unless we duct it to a final destination. If we put it in a common space, we don't really have any control how much gets into a bedroom, a living room, a kitchen, or an exhaust. And generally kitchens and bathrooms, we want to pull air out of rather than put it in there.
Yeah.
So there might be an operating bath fan in there. There may not be an operating bath fan. If there's a bath fan that's unregulated, that we're pushing air into the building and it's scooting itself out of the bathroom, that means there's a clear travel pathway into that room, and maybe not so much air is getting into the bedroom because it's all going to follow a path of least resistance, which means CO2 levels in the bedrooms are going to be unpredictable and rather high. Exhaust only is the same story. We set up some simple ductwork. We remove air from certain spaces. We don't really have control over where it's going in and out unless we run ducting to control where it's going in and out. And we need a building envelope that will allow some recovery air to come back in if we're going to get the airflow to really work. And generally, we're not looking for a building envelope to have lots of leaks and so forth. So those two concepts are kind of fighting each other. Same thing happens with CO2. There's an issue around moisture and managing moisture in kitchens and bathrooms and cooking smells and so forth. And studies have shown that things happen in buildings that we don't really see. So this is just a quick study in exhaust-only ventilation in New England. If you start measuring how much CO2 is in a bedroom with an open door, you'll see low numbers like the first green bar, night 1, door open, the house has got a lot of volume, there's fresh air to mix, and the CO2 starts mixing out of the room. As soon as you close that door in all of those homes in that study, then you've got people making CO2 and you've got no replacement air coming in, and you're not exhausting the CO2 out because there's no drive to exhaust it back out. Next, and it goes to very alarming levels. So this area right around 2,000 parts per million, right? That first bar above the red, that's where you literally fall asleep in class. 1,000 is worrisome. 1,000 is recommended. Where we typically live is halfway between 1,000 and 0, right about 500. So, 1,000 is okay. It's not recommended to go higher than 1,000. 2,000 is really, really not good. 5,000 is downright unhealthy. And so without ventilation, those are the conditions we're living in. We're strong humans. We can deal with it, but we know how to make things work better.
Albert, that's pretty disconcerting at 5,000, that if you sleep in a bedroom with your windows closed and your door closed, you could be experiencing 5,000 parts per million of CO2 concentrations. What long-term effects on the human body does that have? Do we know? I can't answer that question. I can't answer that question. I don't think it's good. Yeah. But Rod, great question. Wish I had the answer for it. Yeah. Okay. The immediate issue is really not a very good night of sleep, right? We need oxygen. We don't want to be overwhelmed with CO2. That has to do with our cognitive ability and general health in that moment. And what the long-term accumulation is, I can't really say, but I know that you're not going to be sleeping well and you're not going to be comfortable. So the next night, so we can see kind of what happens. Doors open, things get better because we've got a large volume to mix and get fresh air in. Doors close, not so good. And again, when the doors closed, we're trapped inside the home with all the potential pollutants we've brought inside of it. So balanced ventilation is really the best answer. It's my favorite way. So the green plus signs is where we're ducting fresh air. So we're bringing fresh air from the outdoors. We're running it across that heat recovery core if we have an HRV. And so we're flowing that air into the bedroom. So when we close the door, we got lots of fresh air. We undercut the bedroom door. So we've got a way for that fresh air to leave after we used it for breathing, because it's going to get pulled into that hallway, which is a common space. It'll travel across the hallway to the negative pressure points that exist somewhere in the house. Doesn't matter where they are. It's simply positive pressure points and negative pressure points. And positive pressure points will travel across the home to the negative pressure points, and then they'll get pulled out. And that's basically how we can route fresh air into a building and prepare to pull exhaust air out of a building at a simple, steady flow rate, running simple ducting and a simple set of fans. And if we throw heat recovery on top of that, then we just need to heat less or we need to cool less. Wow. So really simple stuff, totally accomplishable, and should be really part of every home that we build. So factors to consider, airflow is measured in CFM, cubic feet per minute, and the supply rates for the number of occupants in residential applications is roughly 15 CFM per person. So in a home of 4 people, we generally would want to put 45 CFM into that. I'm sorry, 60 CFM into that home. Yeah, thanks. And so I've got that clock and that 1/3 kind of sitting above that roof. There's a few different ways that we look at airflow. So we look at it as a per person basis. We also look at it as how many baths we have, and we want to run a certain amount of exhaust level to keep airflow coming out of the bath and turning over the home. And then generally, we want to turn over the entire volume of the home once every 3 hours, or 1/3 of an air change per hour, roughly speaking. And so part of the work in ventilation on the ventilation side, if you're working with somebody, is they're looking at how many people are in the home, maybe times 15 CFM. Then they're looking at how many baths and so forth, and there'll be a 20 CFM exhaust rate per bathroom. And sometimes those numbers will align and be the same value or near the same value, and that's all good. And then
The third way of looking at it is maybe turning over the volume, a third of the volume once every hour. And typically those three values will all align and set an airflow rate. If we want to dive in and really do some calculations, then we can look at range hoods, we can look at bath fans and how long they run. We can look at total air changes per hour and try to hit that 0.3 air changes per hour. But in the end, there's a chart. And so at minimum, we want to follow our chart that is really designed to kind of keep us in a safe space. So Rod, if we're in a modest home, there we go. If we're around 15, that 2,000 square foot home, I think you were talking about, and it's got 2 to 3 bedrooms, then the chart's going to tell us we're going to run about 60 CFM, and 60 CFM. The other way I look at it is I got 4 people in a house, 15 CFM per person, that's 60 CFM. I got 3 bathrooms. Generally, if I have continuous ventilation in a bathroom, the code requirement is 20 CFM, continuously running all the time. Right. So 3 bathrooms at 20 gives me 60. So we're in alignment there. And then 2,000 square feet is probably about 1,800, 1,700, maybe 1,600 cubic feet. I can't look at my screen and compute it in my head right at about the same time, but that's going to be 60 CFM is going to be probably on the low side of 3 air changes an hour. So if I wound up bumping it up, and in a passive house, I probably would bump it up. I'd do a more detailed analysis. This is really representing what the code minimum flow would be. We could have a little more, and increasing that by 20% or 25% would be just fine. Decreasing it would not be good. So with that, that's kind of a quick tour of ventilation. And from there, do we want to start with any questions or kind of other topics?
Well, I think questions are definitely in order. And if anybody has a question, please unmute yourself, direct your question to Albert.
Okay, I have a question.
Fire away.
Trying to remember what the heck it was. Oh, so you know that these days we like the Panasonic Whisper Quiet fans, right?
Yeah.
That's what we put everywhere. So are they, I can't remember the CFM on those, but are they 20s? Is that what they are? Are they about 20?
So usually about 50 to 60,
50
right?
to
Because
60.
it's intermittent, right? And so when you get a bath fan that goes on and off, you
Right.
run it at a higher flow because you're not running it all the time.
Right.
If you're running it all the time, it's 20. If it's intermittent, hooked to that switch, 60 is the minimum.
So they're hooking them up now to run intermittently, I take it. So they come on and they can be timed. I guess do they have a built-in timer to them, or is that a separate time switch that has them cycle certain time?
There are all sorts of, there's different ways that they're configured. And in most existing home, it's just a switch that you walk in and you turn it on, and hopefully you run it for 20 minutes and then turn it back off. Because the point is to pull the moisture out of the bath after showering or something like that. They can be hooked up to a system that will run it on a cycle during the day. Here's a fun fact. So if you have a bath with a 50 or 60 CFM fan and you run it 4 times a day for 20 minutes, that is, pardon the boring math here, but 60 times 20, 1,200 times 4 is about 4,800. Thank you. Okay. All right. So if you're running continuous ventilation, right, you've got one of these HRVs and it's running 20 CFM 24/7, you're going to be running more like 12,000 cubic feet per day out of that bathroom, right? So running that smaller number of 20 CFM times 24/7 gives you a lot more airflow out of the bath. And so sometimes what happens, people get kind of worried that they don't have this big bath fan. They've got this small little vent and they're not really controlling it and so forth. And they don't really stop to think that in the total 24-hour cycle, it's going to be pulling a lot more air out of the bath, and it's going to manage it a lot better. And what you find out is that when you're running that much airflow out of the bath, the whole bath feels different. The towels are dry, the shower stall's dry, and it's a completely different environment.
Totally different environment, which reminds me of about 20 years ago, I remodeled about 186 bathrooms.
Okay.
In a 4-month period at Tropicana Gardens, which is a 9-building student housing development. Been there a while with cafeteria and everything. 9 buildings, swimming pool, parking, all kinds of parking, 3 stories, some of it in Isla Vista near UCSB. And one of the things we were tasked, one of the line items we were tasked with doing is putting in new mechanical ventilation, ducted mechanical ventilation. They had ceiling fans in every bathroom that were so wall, and actually they weren't ceiling fans, they were high wall registers, right? High wall register, a fan going into a stud bay. They created a 3.5 inch by 3.5 inch stud bay, no ducting, and that stud bay exhausted to the roof. It was nasty. You couldn't take a piece of tissue paper and hold it up to that fan and have it not just fall to the ground.
Yep, I bet.
It was unbelievably ridiculous. And the bathrooms were all just cruddy and mold and you name it. And now 20 years later, the new, brand new fans we put in those bathrooms don't have any mold, and they're just in a lot better shape. I mean, that's just a simple example of ventilation. But what makes me think of is that bath fans, to do a couple of things. I always like noisy bath fans, so that you can do your business in the bathroom and everybody hears the fan, right?
Right, yeah.
But you don't want to leave that noisy fan on like your noisy exhaust fan in your kitchen all the time. So for what I'm thinking of is that I do have a 2 whisper fans in the main house that is leaving them on more. It's just a good idea. And leaving my forced air unit on fan only and changing the filters are cheap. Super cheap for what you get. But really, I'm a believer. You guys in 3 short 3C REN presentations, you've made me a complete believer. My next purchase is this HRV for my house.
Yeah, that's the thing. It's a complete game changer. I would imagine when you opened up those walls and all that moisture going up into the attic and so forth, it's really hard on the building, right? So it's not good for people. No. It doesn't really work, and it helps prematurely destroy the building. And ventilation is such a simple thing. It's a fan, some ducting, you add heat recovery onto it and you run it continuously. Because, Rod, if you get that noisy bath fan that covers your sins as you make them, you don't leave it on, right? Because you don't leave this noisy thing on, which means you don't run it long enough, which means the moisture doesn't get out of the bath.
Yeah.
And balanced ventilation, nice quality HRV, balanced ventilation will make the building live longer and make everybody enjoy the building a lot more while they're in there.
I'm totally a believer. I was talking to Sean this morning. Sean, he might still be here. He said he had to go somewhere. I was talking to Sean this morning and telling him that this whole thing, the whole idea of having a 4-degree temperature change, if you do the HRV system, for me, what it means is when I came into my house today, because we have a master suite and we have an ADU that we sleep in, then we come into the house and the house I have a wireless thermostat and a well done forced air unit, and the thermostat said 66 degrees. That's the ambient temperature of the house where the thermostat was. And if I'm going to heat my house, I'm never going to heat it to, thermostat to 70, up over 70, maybe 68. But within that 66 to 70 difference, I don't need to turn it on. I don't need to turn it on. I don't need to burn gas. I don't need to create greenhouse gases. I don't need to think about clean energy because I'm not using clean energy. So it really makes sense, and it makes sense across the board.
You know, the cool thing today, the coolest thing for me today right now is that we really have the opportunity to make buildings work like you're describing, right? If we want to make them run between 66 and 70, there are ways just in every step and consideration on how well we think about this building and do our various occupations, including hanging the siding, nailing off the nail pattern, just getting the air tightness down, how well we put the insulation in, what windows we choose. We can make buildings that work really, really well, are comfortable and don't require much energy and don't require any fossil fuel energy. It's just simply something we can do. We haven't done it before. And frankly, it's a really exciting time to be in the industry because we have this new opportunity for new ideas and new technology that is a lot more than just putting parts together on a building, right? We can be creative, dynamic participants in the construction of some really cool stuff.
Yeah, and do it passively so we don't, we do it one time. And then it just continues to save us money and save the planet energy. And it's just, it's definitely a workable thing. It's where we're going to. Questions? Anybody have questions for Albert before we let him get on with his day? And his lovely wife, Eva, that's really contributed some great comments. Thank you so much, Eva, for your comments.
I don't know, do you know anything about, I know this is about homes, but do you know anything about like vehicles and cars? Because I just, like the filtration system and the ventilation system in cars, I just remember back to when we did have those nasty wildfires in December, I think it was 2017 or 2018 here. And my car, like every time I turned on the fans in my car for like almost a year, I could smell that smoke and that ash. So is there like some sort of new technology as well going into cars, like HRV system or something like this that's going into vehicles now? Do you know anything about that, or Tesla's?
So yeah, Tesla probably has a filter.
Don't you have a cabin filter, Monica? I mean, most of us newer cars have cabin filters.
Right.
So have you asked about that?
Not all.
About that?
Not all. Right. Yeah, not all.
I don't know. I'm assuming like my car's not that old, but I get it serviced like every 6 months or whatever. So I'm sure they change the filters when they do the everything.
Don't be so sure.
Yeah, right.
But I just remember thinking like every time I got in my car, I need to roll the windows down because that smell's coming back. Like that I could smell that it wasn't healthy. Or maybe it was just lingering, Yeah,
you might want to actually check your filter too, right? Because you would be capturing all that smoke when your fan's on and when you're driving into air, pushing it up against the filter. So you might have a really dirty filter in there. Some cars do have cabin filters. Yes.
What's your car? What kind of car you got?
A Honda, 2015 Honda.
You might have a filter.
We'll be willing to bet you have a cabin filter.
Yeah.
I'm tasking you to ask the Google gods if you got one.
Yeah, there you go.
I'm pretty sure, yeah. I mean, it's not there anymore, but I just remember it kind of after a long time after being like, that can't be healthy, like to be breathing that in every time I get into my car.
No,
but yeah. Oh, Israel had a question about that. Go ahead, Israel. You're the same in your car, Israel?
No, I said I have
Go ahead.
No, I said I have an answer for that, and they all have like filters in them. Yeah, so it's really easy to replace. They're usually under the glove compartment.
Okay.
That filter and that smells goes away.
But
yeah.
Filtration.
So should you every time there's like a wildfire, should those be changed out? Is that what it is? Yeah.
Usually you replace those like every year because they get dirty really fast because air comes out from outside through that filter. So yeah, you have to replace those like once a year.
Yeah, or more if you're driving around in smoky conditions. I mean, you're drawing your makeup air into the cab of your vehicle from outside, from a road that's full of dust and all the particulate matter in the whole damn world. So you really should be filtering it. And if you're driving in dusty conditions or smoky conditions, you should be changing your filter more often. And mine, in my wife's Prius, and I think in my Lexus, are right behind. I have to drop the glove box and pull it out. And it once you figure out how to do it, it's not that hard to do. And back to when we were having the fires, I was running my forced air unit in my house all the time, and about every 3 days I was changing my filter. So it was costing me $2 or $3 every 3 days. But every 3 days, I was going from a pure white filter to a dull gray filter in 3 days, just packed with the stuff that could have been in my lungs.
It's, I find it funny, right? We have, all of our HRVs have filters, forced air furnaces have filters, car have filters. They're the thing that get the least amount of attention. They want to be changed regularly.
They do.
And they're such a good thing for us. And we're actually privileged to have filters across forced air systems and HRVs and cars. We just, it's sometimes we just got to wake up and say, this thing is there for my benefit, and I should just go change it and keep it maintained.
Yeah, no, filtration. So, drawing in air and exhausting air, and then that whole transfer, the heat recovery ventilation system is are the really good components. But you got to filter the air. We have to filter the air. We have too much going on not to filter the air. And Jay said something in talking about the passive houses, about how if you do a passive house, if you can make your house airtight, right, and do these systems, you will stop having to dust.
Yeah.
I was going, what? Because I can dust today and tomorrow I got to dust again.
Air tightness, right?
Yeah.
So it's down to air tightness. And it's also down to filtration across the HRV.
Yep.
And then also, Rod, if you think about it, when you build a passive house, you need less heat.
Yes.
And so you're not running a big forced air system, which is stirring up a bunch of stuff in the house and spreading it around. Yeah, that's a real thing.
Yeah, no, it's a really good thing. It's really glad to be thinking about it and talking about it, because I've been a real proponent of forced air systems, and I still am in terms of efficient heating, but but now my mind's been expanded. My consciousness has been expanded to a whole other level, because I know we've got to have clean air. The whole idea of air, and it's tough for people to relate to. It's hard to sell people on air quality because they can't see it.
Right.
It's like, why should I do that?
Right.
I think also, like, it's like we live in California, we live in Santa Barbara, California. Like, really, it's a hard sell. I mean, a hard place to relate for most of us, because we don't turn on our heater that much. Most houses in Santa Barbara, older houses that we live in, don't have like air conditioning, or don't have a system, an HVAC system running through it. So like, it's really hard for, I think, us to relate to. But like, if this is the future of where building is going, then we need to know about it. It's just like, it is hard, because like I sleep with my windows open all year, like I don't really like have something running during the, like a heater running at night. Like if I lived in Canada, maybe I would. So, but I get it, because it's a greener, more healthier way to live and build. And I can see like
the challenge for me is to kind of make that relationship with your climate, because you truly are in the sweet spot of the country where you don't need a lot of heating, you don't need a lot of cooling. However, we are in buildings. The buildings do use energy, and we do want to kind of limit the contaminants that we bring in and create lots of, fresh air and so forth. So, sometimes you got to be able to close those windows if the conditions are not right outside, and still get some good air quality and filtration. So, I get it. It's a challenge, and it's really climate dependent on how deeply and quickly you go. but it
Yeah,
matters.
when I
everywhere.
when I think about those wildfires, like that's when I think like for us living here, it's super relatable because it's like Rodney was saying, we had to close all the windows and doors for those couple weeks, and it was hard. So like when I try to think about how this will help us in this area, like wildfires aren't going away. Unfortunately, that's a part of our planet now. So I mean that in that case for us here in Santa Barbara, that's super relatable. You know, we have to
Right.
sometimes
We do.
breathe indoor air.
Yes. Now, do we have any more questions for Albert or Eva? So I want to thank you, Albert, so much, and Eva as well for coming and spending your time with us. Been super informative. Really enjoyed it. Hope we will see you again. I'm going to have you. Hopefully, you'll still be associated. I'll have you present again for my classes coming up. It's all
Great.
good stuff.
Yeah. Be happy to, and you can give me a nudge on what we want to talk about, and we'll be happy to keep it light, go deep, whatever you like to do.
And if you have that PowerPoint and a PDF, if you can send it to me,
sure can.
That would be cool too. You can do it through. Sean's got my email ID. You probably should have it too on the threads, but then I can distribute it because the PowerPoints have been enjoyable and usable for myself and the other two instructors that I teach the CT in the CT department with. So thank you again, Albert.
Yep, you're welcome.
Thank
Thank you,
you,
everybody.
Albert Brooks.
Thank
Albert,
you.
Everybody have a
Thank you,
great
Ava.
day.
Thank you, Albert.
Enjoy
Okay.
building. Building is fun.
Thank you,
Okay, thank you.
Albert.
Thanks.
You guys, all y'all, you guys and girls, we're gonna take a break. We're gonna take a 10-minute break until 11 straight up. Come back at 11, bright-eyed, bushy-tailed.
Do you want to pause the recording, Rodney?
Thank you.
You're welcome.
Rick is on top of it. Start recording, and again, I'm gonna go to screen sharing. What do we got in the chat here? The climate change. Yes, I agree. Let's go to. Now, where was I? Okay, here we are.
We put it so that the wire comes right up so that the insulation just touches the outside of the screw down plate. You don't want the insulation to go behind the plate.
That's right. If you're running wire and you're connecting wire to where the wire goes on, in this case, an electrical outlet, you want almost none of that copper wire shown. You want insulation to stop at the where it attaches to. So this is acceptable. Before, when this much copper was exposed, is totally unacceptable. You're just asking for a short, and a short could ultimately lead to a fire.
Plate has to push against the metal part of the wire. So you only stop it right at the edge of the metal plate there. Looks a lot better than the way the original builder did it. Okay.
Huh.
That leaves you with a nice clean bundle there, so if anybody ever touches that, they won't get shocked.
Now, wrapping it with electrical tape, that's never going to happen. You might do that at your house, right? You might do that at your house, but you're not going to see any electrician do that, ever.
Focus your attention on the back. You'll see I plugged up those two holes there. Plus we went ahead and smoothed down with some silicone here around these cracks here, so the cigarette smoke won't come in from the next door neighbor's condo.
So besides what he just said, in sealing around that box, which a lot of your boxes aren't cut all that tight, some of them are, depends on your drywaller or how old the place was. It's a place that leaks a whole lot of energy, not just your next door neighbor's smoke getting through the box, but particulate matter and dirt and all kinds of stuff can come through there. And that's why they're using foam now to insulate around boxes as well. And you see he's put some silicone caulk in those holes. So he's filled up the holes that could transfer heat, cold, and particulate matter.
So I think the smell is pretty much gone now. So we've successfully at least kept it coming in from this spot. So you get 2 repairs on one here today.
So the cigarette
Okay,
smoke?
so there we are, the Dakota switch is all screwed
One
in.
apartment building into the next to the air shafts?
The smell, yeah. Through, well, if there's some crossover from the ventilation system, but the common, that's a hole in the wall. That guy, so it's maybe a common outlet, so that guy's smoke is getting into the wall, and it's like, maybe you have more negative pressure, you know what I mean? You may have more, he may have more positive pressure, so it's just pulling it, from his apartment, that smell of smoke. And apparently, after sealing up this box, they were down there apparently smelling the cigarette smoke. After sealing it up, they couldn't smell it anymore, which is great.
Okay?
Because
Always remember,
I don't know if any of you smoke cigarettes, but if you do, stop right now. Throw your cigarettes away. There's better things to smoke.
screw it in, always remember to look and make sure it says top. Now, you probably can't see there, maybe you can, but engraved in the middle there, it'll say top. And that's how you know your switch is right side up. Otherwise, you'll plug it in, screw all the plates in and everything, and you're gonna find out that your switch was upside down. Okay, now this step is what differentiates what we're doing with what everybody else does. We're
Yeah.
putting this little gasket in here,
Yeah,
and that also helps seal.
yeah,
It keeps your air
Yep.
conditioning from escaping out through your
Yeah,
outlet and
yeah.
into the wall. And it also would seal in case there was any cigarette smoke in there.
so this is something you do not see people do around here. And I'm gonna find out why, because this seems like a really good idea. Now, you wouldn't need this so much if your boxes are cut really tight and there's no excess holes in them. They're just one place for them to come in, and maybe they're foamed around. Maybe you don't need this, but as a retrofit, these gaskets look like a really good idea.
Next door neighbor. So when we put the plate on here, it's gonna squeeze this gasket up against the wall and cut everything off. There's no air is gonna get in or out of here.
Good idea, really good idea.
And I always use these metal plates. I like these. These are super wide. They're wide on the side and taller on the top. So that'll help you in case you ever have any holes that were cut in the drywall too big. And these metal plates are good because you can see there's a little bit of.
And then the only thing about those oversized plates, metal or plastic, is that they are butt ugly. Your eye is so used to seeing a particular size plate, right? That's what you see everywhere. Your switch plates, your duplex outlets plates. And then as soon as you see a big outlet plate, my head says, oh, mistake. They made a mistake. They got to cover it with a big outlet plate. So it's a small detail, but I'm not for these big outlet plates.
Curvature to the wall here. So I can screw this better to the wall than a plastic plate. The plastic ones will crack. And there is your finished product.
Maybe the.
And I know
the
I
bigger
like to
plate
leave
has
both of my
something to
screws
do with
pointing.
The gasket. Is maintaining it.
Oh, this one, the bigger plate?
Yeah, because he was saying if you had a plastic one and you're trying to screw it in, like if you're trying to screw it in tight, you might crack it.
Yeah, and you very well might. I've cracked more plastic plates than I can count. But yeah, so maybe it is a function of the gasket.
Better. You can see it's nice and snug here. There's no more cigarette smoke coming in from the next door neighbor's unit.
That's just, ugh.
Okay, so we have this electrical outlet here in the bathroom. You can see how close it is to the sink.
Yeah.
And we were gonna.
Okay, so GFCI, GFIRC, ground fault interrupt receptacles. Anyway, I might have got the initials backwards, but if you have an electrical outlet within 4 feet of any water source, you are required to have a ground fault interrupt outlet, and he's going to tell us about them.
Take this outlet out of here. We're gonna put a new one in anyway. Our plan was to put in a GFI outlet because it's required by code anyway. Anytime you have an outlet within 6 feet of.
Say again, please?
Are those the ones with the
With the
buttons?
test button, yeah, exactly. So they interrupt the grounding. So if you were to get shocked because you're in a water environment, you wouldn't ground. It somehow interrupts the grounding, and maybe he'll explain it better than I just
Sink
did.
or water, that you have to have it as a GFI.
It's got to be GFI protected. But we discovered something here when we pulled this outlet out. So if you look at what they did here, see they moved the white wire there, common, and they also looped the black wire, and that's not a problem here. Does anybody here see what the problem is? Do you guys see what's missing here?
No ground.
If you look closely at these wires here, see a black wire, see a white wire, and what's missing here?
No ground.
That means this outlet was never grounded. That's extremely dangerous to do that. And on top of that, they probably thought, oh, I'll just screw it to the front of this outlet box and I'll be grounded. Well, that's not true. Probably for a couple of reasons, because it's painted on the front, first of all. Second of all, the box itself is not bonded. That means, see that you can see that in the back there, they got paint all over. These are the ground wires here coming up and through there. They're feeding through the box, but nowhere are they wrapped around a ground screw. So we're going to see if we can't fix that right now by putting a ground screw in there. You can see there's a hole in the back there, right there where my finger's pointing. That is where we can potentially put in a green ground screw and try to wrap some of this ground wire around it. I don't know how whether we'll really be able to. We're going to try our best. We'll have to sand off some of that paint, get it nice and shiny and coppery, and twist another piece of ground wire around that, wrap it to the post, and then have another pigtail ground come off of our ground post or ground screw, and that pigtail will then come and feed the outlet. But the way the previous electricians had implemented it, they totally blew it, dropped the ball, in probably 3 different ways here. But we see this kind of stuff all the time, and we're always ready to deal with it when we do see it. So let's get busy fixing it. Well, you can see here we were pretty successful at finding a good ground here. So what we did was we found the ground wire that was coming through the box. It was coming in from one Romex connector here, and it was going in and coming out, just passing through the box and going up and out through that other one that you see up there. So what we had to do is first had to sand this wire down, and I did that with this emery paper here. This is like a little sandpaper, and that got all the paint off it, made it nice and shiny and copper and nice and bare. And you form a loop out of the wire, and then we stuck it through our screw. We stuck the screw through it and into the screw boss into the box. And then this is our pigtail. This pigtail is going to go to the outlet. So now this is the way the electrician should have done it in the first place. Don't ask me why they didn't do it that way. I just have no idea how builders get away with this stuff, but it still blows my mind how they overcharge you and overcharge you and overcharge you.
And then that was a continuous circuit, right? So that circuit was fed from a power source, that duplex outlet, and then it continued on in its same circuit to probably another duplex outlet. And so that he just opened up the Romex insulation, pulled the ground wire, ran it through the box, and then he didn't even cut his neutral and ground wires. He just wrapped them and kept going. So this guy's cut them, and then we'll see what he went. He sure doesn't like electricians though, does he?
Be above market value for a new house, and then this is how they treat you. It's just terrible. There's no excuse for this. And so this is the proper way to ground it. So what you can see what happens is any ground that came through this box is now attached to the metal body of the box. And electrical code, National Electrical Code, requires a metal outlet box, whether it be a switch or an outlet, has to be bonded to the system ground. And this is how you do it. So now we're ready to go ahead and install the GFI outlet. We just had to do one quick thing here before we put the outlet in. You can see I had to add a lot of silicone and caulk around the edge of the outlet there.
Yeah.
That's how we seal it, to keep the cigarette smell coming in from the unit next door. So, typical with these 55 and over condos, you get a lot of these old timers that just smoke like crazy. Oh man, it's terrible.
Where does this guy live?
Most of it up. But these outlet boxes all have little holes in them, and you can see where I had to put in patches of silicone there to close those off. So there's no more openings anywhere. There's even a couple on the side there. You probably can't see it, but they're inside there on the side. We had to get in there and get at them. So
some of these people, they just smoke like factories, like chimneys, man. And, you know, they take the tar out of their lungs and recoat the whole parking lot.
Hey, hey, dude, that's like, that's smoker racism.
Well, and save the HOA some money.
Man, if I was a smoker, I'd be pissed right now.
All right, so here you can see we've got both the white wires on the left side, and we have both the black wires are connected up on the right-hand side. So the upper two are the line, which go here and out the wall to the fuse box there. And this bottom pair here that you see coming out of the bottom of the back there, they go to the next unit down.
Yeah, so
So all we're gonna
remember,
do,
as I said, they didn't cut those. They just looped them and kept them going. I don't even know how they did it on that outlet. You saw, they just kind of did a little loop. It's just not a very positive connection. You want a positive, you want to cut that wire and bring your neutral to its place on the bottom, and it's your hot, your black on the place on the right on the bottom, and then you want to come out of the outlet to the next circuit. Unless it's a home run and it stops there. Home run is the end of a circuit run, and I hope I'm not getting ahead of myself, but that's the way to properly install an outlet.
is hook this up to the box there, turn the power back on and test it. And remember, when you get these from the factory, you're gonna freak out, go, hey, wait a minute, why isn't it coming on when you first turn it on from the fuse panel? You still gotta hit this reset button because they come from the factory already reset.
Yeah.
And I also wanted to point out to you just one other thing. These are tamper-proof. So they have little rubber things in there that keep little kids from sticking metal objects in there. Anything other than a plug, it shouldn't allow. This is a great time for you to take a look at the subscription button down below.
Yeah, this guy's good. I like his stuff, actually. I think he's pretty good.
Prejudiced against smokers.
Yeah, except unless you're a smoker. So let's look at this one. Let's look at how to create a house wiring diagram. How are we doing? I gotta watch the time here. I got that Rotary Club thing. Okay. Oh, did I bring my? Yeah, I did. Okay, here's a video I thought was very interesting.
Hello everyone, welcome to EdraMax. In today's video, we will draw a wiring diagram of a house with EdraMax software. EdraMax software is a very useful software for the making of many types of drawings. You can easily make any drawings with this software. To draw a house wiring plan drawing, go to the building plan on the left side.
So
here you will find.
I wondered, it sounds like this guy typed this presentation and then told his computer to go ahead and talk it, right? Doesn't that sound like that? There's no way this guy talks like this. This is a computer talking, saying his words. Interesting.
Find some sample templates. Click here on the electrical and telecom plan for this drawing. Now a blank drawing area will open here. Here you can design your drawing according to your plan. On the left side, symbols libraries are given. You can find all electrical and telecom symbols from the libraries. From here you can drag and drop symbols according to the drawing and draw your drawing. I already set up a house plan view here. Now I will prepare the house wiring plan. Here I draw 2 bedrooms, 1 lobby, 1 storeroom, 1 kitchen, 1 bathroom and 1 drawing room. First, we will draw fan and concealed light. For this, we will use symbols from libraries. First I will draw the fan. Now we have drawn the fan according to the requirements. Now in this room, we will draw the concealed lights. we have drawn 4 lights here. Similarly, draw the light in the whole house according to the requirement. Now here you will see that we have drawn fan and concealed light in the whole house. In this room, we drawn 4 lights and 1 fan.
This is a pretty interesting program. I wonder, once you do one, you tell it to do the same thing. I wonder if it populates. I'd like to find out. I like this.
In the lobby area, we drawn 4 lights and 1 fan. You can customize size to select the symbols. And the same thing is done in the drawing area. 1 concealed light is used in the bathroom now. We have drawn 2 lights and 1 fan in kitchen. And the 2 lights and 1 fan is also drawn in the storeroom area. We need to draw a power distribution board. This is a power distribution board. From here, the conduit pipe will go inside every room. We will.
So what he's calling a power conduit, what do you call it?
Distribution board.
Power distribution board is a sub panel, has to be.
Select the connector from above to draw the conduit pipe. For this, we are going to use curved connector. You can change the default settings of the connector. For this, you have to go to File. After that, go to Option, and after that, go to Default Settings. Here you can change default settings into user-defined settings. From here, you can change the color of the connector. And from here, you can also change the design of the connector. Now, we have set the settings of the connector according to our requirements. Now we will draw the conduit pipe from the power distribution board to all fan boxes.
Wow. Okay, so in this wiring diagram, they're wiring wherever this house is. They're before they run the wire, they're showing where the conduits that they're being run in conduit. So in all commercial buildings in let's just talk about Santa Barbara, electrical wiring has to be run in conduit. It can be run in flex conduit, or it can be run in rigid conduit, or EMT, which is electromagnetic something or other, tubing, which is a little thinner wall than a standard electrical conduit. Conduit can also be PVC, but you run the conduit first, and then you use a fish tape to go through that conduit to where you want the wire to go. You tie off the wires you're going to pull, and then you pull wire. And let's see if we get to that here. Hopefully we do. I want to show you that so you understand how this stuff is done. And I think after this, we'll watch the second part of Rich's video, and then we're going to be gone.
You can see that we have drawn the conduit pipe from the power distribution.
And so the really cool thing about conduit is Romex cheaper, right? Your walls are open. It's a new space. You can run Romex, and it's a insulated wire. You've seen it, right? I think Pat's probably showed it to you. I have some here I can show you, but it's got depending upon the wire, it's probably got number 14 wire. It's got a white and it's got a neutral and a hot, a white and a black, and it's got a ground wire in it. Now you can also run conduit. And if you run conduit, the beauty of conduit is you can pull more wire in conduit. So you basically have a raceway in your walls between switch legs and between outlets and between fixtures and appliances. If you're in conduit, a commercial building or your house, some people do run conduit in your house, and you can pull more circuits, pull more wire without opening up walls. People usually don't do it because it's more money, but it gives you more options.
Distribution board to all fan boxes. Now, we will draw the conduit pipe in this room. Right now you can see that conduit pipe has been drawn from fan box to 4 concealed lights for this room. The conduit pipe has also been drawn in all directions for wall lights and switchboard. So similarly, we will draw the conduit pipe for the whole house.
So everything right now that he's showing, it looks like he's run a separate circuit to every room. Starts with powering up the fan, and then that electricity on the same circuit goes to power each of the 4 lights. So each room is on a separate circuit for their lighting and their fan at this point.
Now you can see that we have drawn the conduit pipe for the whole house. In this room, we have given connectivity to 4 concealed lights and 4 wall lights with conduit pipe. And also, we have drawn the switchboard as per the requirement. In this way, we have drawn the electrical house wiring plan. If we have to write any text in the drawing area, for this, we need to select the text option from above. After selecting the text option, we can write the text in the drawing area, like this. Now I am writing the title of this drawing here. You can write any text according to your uses. You can increase and decrease the size of the text from this option. Now our drawing is completed. To save this drawing, we need to go to the file option on the left side. After this, we need to go to the export and send option. Here you can save it into different types of formats. According.
All right, I'm done with that. So we're gonna run out of time sooner than later. So I want you to see the rest of Rich, number 2 on Rich. I think we left off.
It didn't used to be that way, but if you look at the colors, yellow is now 12 gauge, white is 14 gauge.
Okay, so we're talking about the colors of Romex.
The colors, yellow is now 12 gauge, white is 14 gauge.
And it's all 3-wire, right? Neutral, hot, and ground?
Well, yeah, some is a 4-wire, and so the new stuff has 2 neutrals and 2 hots in it. So that's, we used to share a neutral with circuits, but I don't do that as much anymore.
So you see up in here, up on the ceiling, one of the laborers at this job, after the ceiling was isonined, they, in chopping away some of the isoning to get to something, I can't remember what, something had to do with the ceiling paneling, he nicked the insulation off a piece of Romex. So that wouldn't happen in conduit. And because it happened in Romex, we had to open up the wall here. We had to open up the wall here. We had to pull new wire. We had to do all kinds of hoop jumping, which I wasn't really happy about doing.
So you'll still see the white number 12 wire, white number 10 wire out there, but it's all the new stuff purchased is colored white, 14, 12, yellow, and 10 orange.
Okay, and y'all remember that the lower the number in gauge, the bigger the gauge. So 14 wire is smaller than 12 wire, 12 wire is smaller than 10 wire. Can you tell me what in the heck what's the neutral do? I mean, can you tell us in layman's terms how that works? I mean, I can picture a hot wire, live, right? Electricity running through the copper wire.
It's the return path for the current, so it comes in the hot and back in the neutral, right?
Okay, goes in the hot, comes back in there, so it's a circuit. You can interrupt that circuit with a circuit breaker. And circuit breakers are made to, and they also give you overload protection and heat protection too, right? You trip when it gets too hot or.
Arc fault breakers that require no arc fault GFI breakers. Arc faults made a difference between the ground bare wire and any differential between the ground and the neutral will trim the arc faults. Sorry, the GFI is the ground faults.
Right.
The arc faults are read the differential if there's any sort of sparking between the black and the white. So sometimes, even a bulb blowout will cause that arc fault to trip. So we get sometimes a lot of nuisance tripping, but it was really doing its job. It's just picking up an arc, and the arc was the light bulb tripping. But sometimes it's a lamp. They like the old in the bedrooms you used to have a 2-wire lamp, 2-wire cords plugging a lamp fixture bed. Those cords would get shorted and they start to trip. I think that's part of that arc fault.
So our arc fault I know GFIs are required anywhere within 4 foot of any kind of a 1%
No, it used to be
fixture.
60, but now it's pretty much anywhere It's either a GFI or an arc fault, pretty much
Huh.
everywhere.
Everywhere.
I mean, except for some specific equipment.
And those are outlets, duplex and quad outlets.
Yeah.
And it doesn't apply to switching, so.
Switching's on arc fault, lights on arc fault. And in the beginning, arc fault seemed like always trip under lighting, but they don't seem to trip now. But it's really caused people, we have a job recently, we're working with some other electricians, we're doing some computerized stuff behind it, but we got there and none of the arc faults would hold. Well, and it's very common, neutrals get tied together between two different lighting circuits, and if they all lights go together, and everyone thinks, oh, lights go together, put them all together. If they're together, the breakers recognize it, so the arc faults have really helped in finding problems that people would never even have diagnosed before. So it's
Yeah, and then once they're buried in the wall, they're pretty hard to fix. Now, what about the idea of a half hot? Because I know we've got a bunch of them in here, half switched outlets, right, for lamps, not completely switched, but like the top would be hot and the bottom would be switched, or vice versa.
So
Is that pretty prevalent?
Used to be really prevalent, and we still use them a lot, but we don't use them as primary lighting. Here in some rooms, I think she uses it as a primary lighting. But what has to happen if you want to have it on a dimmer, you have to use a specific outlet that'll allow the outlet to dim without burning up a vacuum or whatever. So if you use a standard outlet, anybody can plug into it. And if anybody plugs into a dimmer, it'll burn up whatever they're plugging into it, ruin it.
So basically, if you wanted to put your lamps that were plugged into your half outlets, which were controlled by a switch, and you wanted to have that be on a dimmer, you have a few other hoops to jump through to make that happen.
We use a specific device for the outlet and a specific cord end on the lamp.
Wow.
And then the dimmer will do it. So then the lamp will plug into it, you can dim it up and down, but no one else can plug it. Vacuum.
Which would suck for your vacuum. I mean,
vacuums.
And that's not a good thing for a vacuum. You might think it would be, but it's not. Yeah, so, and you guys ran this, so that's another thing, I've seen a lot of jobs where, I mean, this is a clean job. Some of the stuff that, this is when you watch an inspector walk around, they want to make sure your Romex is tight.
Yeah, not so tight that it damages the wire, but tight enough that it doesn't fall. You know what I mean?
And also tight enough if you happen to be icing in the wall that it doesn't
push out.
Blow out.
Well, one of the things is, in the code and all of our rules and inspectors, it says in a workmanship-like manner.
Mm-hmm.
Well, that's kind of up to the person, right? And it's up to the inspector to enforce, but I push my guys to make it better, and always trying to do it better. And, they get tired of hearing me, it's not good enough, but that's super important to me. I know if they care about
Are these adjustable boxes?
These ones are, some are.
Because it ain't 5/8.
That little tab right there is supposed to be that's actually the half-inch tab. So it's a little further than average tab. That's a 5/8 drywall. And, that's another thing. You just probably drywall. We use 5/8 drywall here, right? I mean, I've been working here for years. Everybody uses 5/8 drywall. If you get out of Santa Barbara, you get in the city there, it's like, really? We still use half-inch here. Where I'm like,
Don't use half-inch anywhere.
Yeah.
And it's not Type X 5/8 is the 1 hour firewall, a half-inch isn't. So.
Yeah. So I don't know why that is, but I know a lot of counties or states are using that. Out of California for sure.
Yeah. I'm just super. I thought you guys were going to strap a whole bunch of stuff. I wasn't even thinking about how much.
We did it behind it.
Well, you have some hid behind there. There's a gas pipe behind there, and this Smurf tube, which is taking data stuff, right?
So yeah, I think you ran the data stuff free, and then left the empty Smurf tube for a future.
Okay, right,
from this side of the building to that side.
Right, so that tube, that orange tube is a conduit that's available to pull new wire from one side of the house to the other, because this is all volume sealing. And once this, without that conduit, if they want to run any new circuits for any reason from one side of the house to the other, because of the volume ceilings and no attics or crawl spaces to get to, we would have to open up walls. So with this conduit, we have a channel to bring wire for new circuits from one side of the house, from the side of the house that has the panel on it, the meter, to the other side. I'm telling you, you're not going to be able to run anything without it showing, but I'm just still amazed with as much stuff that was up there, that there's that many circuits.
Well, there's another thing. I mean, I don't know how everybody else does it, but it just seems like a lot of guys have extra circuits on their panel. And I'd love to have a lot of extra circuits on our panel, but when I run things, the amount of circuits we run, it seems like we often fill up a lot of the panel. But, you know, we don't get a bunch of overload tripping all the time.
No, and you don't get it where people turn their god dang microwave and.
Right, and I don't want to call my breaker trip. I said,
No.
hopefully if I wired your house, I'm not getting those calls. I
Yeah.
told someone before, not your number, I said, you have the office number, but hopefully you won't need my number. Forget it, right? You won't need my number.
And no, I don't want to give it to you either. See, is it anything in here that, I was so impressed with those runs. Those, what did you call them again? Those things with all the holes in them that they.
Home run helpers.
Those home run helpers. I can't really see them from here, but there's just a whole plethora of
They don't
them.
work everywhere.
I think we had them up here as well. I saw a bunch of them. So you guys, in wiring this house complete, because there's no stone left unturned here. There are no old boxes. No old wiring, all new circuits, new outlets, new switches, new lighting, new fans, new everything. Because I gotta say, I'm gonna ask you something about it. What, were there anything particularly challenging about this house at all? Is it pretty standard? I mean, other than getting across.
Just getting, not being able to use this, which was attic space.
Right.
So getting across here is fun.
Which is a big deal, because normally in a regular house with cyclone truss line, this bottom cord, right here, that bottom cord, that's what takes the ceiling drywall. And then this is all attic above, which you can run. You don't have to be all that clean about it either. You can just run it forever. And nobody really cares because nobody's going to go up in that attic. Now here we have a fairly small attic space and not a whole lot of electrical up there. And then over in here, what did I see in here? God, I mean, look at that. I've never seen these before.
Those are called stackers. Those have been around a long time. Those are what they used to use before the other ones, and instead of staples, and they're pretty good. They do fall loose sometimes, so sometimes even though, but you won't see much of that. I mean, typically guys don't just tie, but typically none of my guys are trying to please me, so they'll close the tie like that.
Well, they're really, it's just clean. I mean, everything's really clean. And these guys are circuits for the
I told the
air
guys,
conditioning.
does it take any longer to drive than it does to drill a crooked line? I mean, it really doesn't if you just have a little bit of a plan.
Yeah, like these lasers, everybody's so fond of breaking out.
I grew up, we just stuck, this little different height here, but we just stick it on our knee, and every one it's on your knee, every stud you're on right on your knee in the same spot, it's in a straight line.
True. Rich, do you know what this box is for up there?
That's the smoke detector, which has to be.
Of course, it has to be a wired smoke detector, right?
Yeah.
Within how far of the peak?
Each manufacturer is different. The last inspector asked us to bring the manufacturer specs because they've been different. But they used to be more than 12 feet down. Some of them are between 4 and 12 feet down. Some are different from the walls than the peak of a ceiling.
We had to move that because it was within 3 feet of that supply air register, so we had to move it over.
You're in the triangle or below, so it's really good to reference your manufacturer.
This is another thing I've seen you guys do a lot, which is get spare and empty Smurf tube / conduit for future data runs to places that were going to be virtually impossible to do cleanly without opening a wall. So now what you've got is that tube would get data all the way from the panel, all the way from your kind of main control data box. It would get data, you'd be able to pull it to here, to this spot, all the way across. After the house is completely done without opening anything up, which is a pretty dang good deal.
Right. Well, no one thinks they want anything when they're building a house.
Right.
It's a budget, and they're just trying to be careful, and then later, and then move their furniture and they're ready to do.
No, it's really great that you do anticipate that. Really appreciate it a lot. And just the job is so clean. So if you guys haven't been picking up your wire tailings, somebody has.
What's that?
If you guys haven't been picking up your wire tailings and insulation, somebody has.
We've been trying to be a lot better through the years, because, channels had crews on the job site and that was part of the cleanup.
Right, right.
Now, all the kids come from college and they run the job sites from the paper and every sub is responsible for themselves kind of, and it's a little different.
Yeah.
It's changed quite a bit.
It's a little different. Well, Rich, it's been a pleasure interviewing you. Rich is my electrician. He's the only guy I ever want to use. And it's because he does things right, usually the first time. And if he doesn't, he's willing to come back. And he's really helpful. And he's got a good personality. So, Rich, say goodbye to City College. Thank you so much. Great guy. Great electrician. Okay. All right. Hey, everybody. It's we now only have less than 15 minutes left in this class. So we're not going to break out into rooms, but I did notice that in the breakout rooms we were doing that, Monica's room always had a bunch of cool stuff going on. So Monica, do you want to give us a screen and type some stuff on it like you've been doing with your breakout room so we can all sort of participate in that? You had some great topics on your screens always.
Sure, I can do that. Yeah. I'm going to share screen. Let me get a new sheet coming up here.
God, I hope I sent myself the Zoom link for that.
Okay. So what we usually do in our breakout room, for those of you who are here, is I'll share a screen and we'll go over what we've talked about in class. So we can, if anybody wants to comment on the guest speaker. So we had Albert Rooks. His company is called, what is it called? Small Planet Supply. Okay. So he said he's based in the Pacific Northwest, right? So he's up in Washington State. Washington State. Okay. So any comments or questions about what you saw in the presentation, something that you noticed, or something that was relatable to you guys in the presentation about ventilation? So he was going on about his push is for the passive house. So do you know what a passive house means? Does anybody get it? What's a passive house?
Well, I know what a passive aggressive house is.
Yes, I was thinking, so there's a push to be aggressive and there's a push to be passive, right? So a passive house basically means that the ventilation is tighter, right? So where are some places in a normal house, in an average home, where are some places that air seeps in or out? Where are some common spaces?
Under doors.
Under doors, okay, so cold air can come in, air can go out. What else?
The living room.
In the living room?
Yeah.
What specifically, what part of the living room does air go in or come out?
The entrance.
Okay, so the entry, the front door.
Yeah.
What else?
The vents.
The vents, okay. So all the vents.
Windows.
The windows. So think about your house and your windows or your doors, or where are places that you think air comes in or out unintentionally.
Gaps, cracks.
More poorly installed electrical.
Yeah, so that's what he was saying, the electrical outlets, right? Any place that there's electrical.
Yeah.
Is if it's not done tightly or in the way that he's saying this passive house way, then that's another spot, right? So electrical outlets, any place there's electrical.
And also to have an HRV, you need to have two filters. One for incoming air and the other for leaving.
Yeah, and
the
that would be
system.
an HRV system. But, and let's get to that in a second, but just another big one, because a lot of homes, in the last, 40 years have down lights, can lights, right? Halo cans, 6-inch or 5-inch halo cans in the ceiling. And if they're not installed properly, if the openings are cut properly, if they're not insulated around them, they're huge because they're up in the ceiling, right? Heat rises, second law of thermodynamics, and rises up to an unconditioned space. So you are losing energy through your can lights big time.
Okay, does everybody know what can lights are? Does anybody have can lights in your house?
There you go, just like that.
Okay, so basically, I've never lived in a house with can lights, but I know what they are. But basically, it is into the ceiling, right?
Yes.
Yeah, so I think we've seen a couple videos where they're installing the piece that holds the can light. So what happens when you install that piece? There's air seeping in, right, through the can lights.
Yeah.
Like these kind of recessed lights, I guess. So Rodney's saying this is pretty common nowadays. People want these can lights, but if you don't install them tight or in like they do in maybe in a passive house, then there's space for air.
And that's a typical can light. That's where the can light comes from.
Yeah, this is the word can, right? It looks like an aluminum can.
Yep, exactly.
Okay. All right, so anything else? Can lights, electrical outlets, anything else that Albert mentioned? Where?
I can't think of anything else.
Okay, so what else were you saying? You were also saying about like your attic space or your crawl space under your house. So what happens there, everyone? Like if you have an unconditioned attic space or unconditioned crawl space?
That cold or hot air will leak into your house, or hot air will leak out, cold air will leak out, cold air will come in, hot air will come in.
Yeah, so think about that, your attic space or under your house if you have a crawl space.
Yeah. Sealed houses. I mean, they touched on Mr. Gentry, which you guys didn't see, touched on that too, but the whole idea of airtight houses, which I never was a proponent of, but now I am, creating an airtight house, which is more difficult than it sounds. You basically have to, if you're building a new house or you're remodeling your house and you want to make it airtight, you're going to have to replace the windows and doors with airtight rated windows and doors, which are not going to be cheap. So if you go buy a new window that's thermal glazed, got double weather stripping, and as good as a window you can get, it's not going to be airtight. It's still going to leak air. There are windows that are window manufacturers that are making airtight windows, and I'll find out some more about them because I'm curious is what the price point is on them, because our even brand new windows are not airtight. And
okay.
That's a pretty significant factor in doing a passive house, is make your house airtight, and then you can control what comes in and what goes out. It's all about control, which is what life's all about.
Okay, and then Gerardo, what about the HRV system? So tell us what you learned about that HRV system. You were saying you're muted. Turn your microphone on.
You need two filters, one to take the air in and the other to take it out.
Yeah. That's
okay,
it.
So yeah, there's a supply and then there's an exhaust. Is that right?
Exactly.
Right.
And then the really cool thing is that when you do it the way it's meant to be done, you bring air in, right? You bring unconditioned air, cold air in or hot air in, and you exhaust the opposite air out of your house. And you transfer the airs in the same duct that, the air in runs through half the duct, the air out runs through the other half, and it's separated by a piece of metal, and that metal is conductive. And so as the cold or hot air passes through this pipe, it transfers its energy one to the other. So cool air is heated, heated air is cooled. So you wind up with a system that's balanced right in this HRV system, so that you are keeping no more than a 4% temperature difference in inside to outside air. And that means you're going to be saving tons of money in the heating and cooling. Of course, as Monica pointed out, in the fact that we live in Santa Barbara, we don't have that big of swings in heat and cold, unless you happen to live in Lompoc. Now, if you live in Lompoc, basically the coldest summer I ever spent, coldest winter I ever spent was a summer in Lompoc. I mean, seriously, I went to a July 1st or, mid-July football game when I was in Kiwanis, and it was our North-South All-Star football game, right? And they said, yeah, bring hat and gloves. Bring your down coat and your gloves and hat. I go, it's the middle of summer. Because just bring your hat and gloves. Man, it was cold. Anyway, I am going to, Monica, could you stop your share?
Yeah. Thanks, guys.
Let's get back. And we only have a couple minutes. Like I said, I want to get out of here in about 3 minutes. So I have about 5 minutes to try to find this Zoom link, which I hope I sent to myself. But just want to say, hey, you guys are a great class. Looks like we lost a few people. That's right. Some people had to go. Some people probably decided it was a time to go, but that's okay. I hope you're enjoying these presenters. I am. This is all kind of cutting edge stuff, and it's all stuff I feel like we all should know about, just to improve our knowledge of the things that are pretty basic to life, like indoor air quality and energy resources and stuff like that. But by the same token, this is entry level stuff. This is rather not entry level, ground level stuff. If some of this stuff interests you or piques your interest, this may be something you might want to think about and talk to us about and talk to your career counselors about. Maybe a place you might want to get into for a job. It's not going away. It's just going to get bigger and bigger. And I'm pretty excited about it myself. And I wish I had seen these things prior to the house I'm building now. I would have put in an HRV system, and now it's a little bit late. I still might do it.
I agree. It was super interesting. The presenters are really valuable. It's nice to have a different outlook as well. Somebody else's.
And who doesn't? I mean, it's kind of a win-win, no-brainer. Who doesn't want to have healthier air quality? Who doesn't want to have a healthier environment to live in? And who doesn't want to have an environment that's less costly to live in? I mean, it's just, and there's some upfront costs, and there's some thinking about it. So I'm glad we're all thinking about it. That's a good thing. So I want to say goodbye and stop the class and give you all this great extra 35 minutes of your day, no charge. Have fun with it. Do something really great, like feed yourselves or whatever, or feed your mind. But I'll see you all the day after tomorrow, right? And we have another presenter, and it'll be our last class. So we're going to have a big party.
Party time.
Yeah. Woohoo!
Okay.
Anybody
That's good.
Like Israel's here today, and Francisco's here today, and Carla's here today. This is our class. Hey guys, hey, look at that. They're here. They're actually here. So if anybody wants to come, you're welcome to. I'll just have to ask you a couple of questions and take your temperature on the way in. Just let me know if you're going to come so I can anticipate. Okay. Otherwise, I'll see you all on Zoom the day after tomorrow.
Okay.
Bye.
Thank you.
Thank you.
Thank you.
Bye, guys.